Hello dear students, this is Milind Patwardhan, your course instructor for the course on mathematical physics. Welcome to 4Pi Academy. So guys, we were discussing the topic mathematical physics, under which we are discussing the topic that is matrices. So in our lecture 4 on matrices, we are going to discuss how to find the powers of a matrix and how to find the exponential of a matrix. So let us look at the first topic, that is how to find the power of a matrix. So we can obtain powers of a matrix by using the diagonalization. We have seen in the previous lecture the method of diagonalization and that method gives us the D, which is the diagonal matrix, as D is equal to P inverse AP, where you know that this A is our given matrix and P is the modal matrix, which is obtained by grouping the eigenvectors. So here A is the square matrix and P is definitely the non-singular matrix, because we need to find here the P inverse, and the condition for inverse matrix is it should be a non-singular matrix. So if I take here D square, then this D square will be equal to P inverse AP multiplied by again P inverse AP. So that will be equal to P inverse A into P inverse P into AP. So since P inverse P is equal to 1, or identity matrix, so this will be equal to P inverse A into A is A square P. So similarly this D cube will be equal to P inverse of A cube P, and therefore in general we can write for D raised to N is equal to P inverse A raised to N P. So if I pre-multiply this equation by P and post-multiply by P inverse, then this equation will become P into D raised to N into P inverse is equal to P into P inverse A raised to NP into P inverse, and this will be equal to P into P inverse into A raised to N into P inverse. But you know that P into P inverse is equal to identity matrix, so that will be equal to A raised to N. So the method of finding the power of a matrix N, that is A raised to N, the method will be it is P multiplied by D raised to N into P raised to minus 1. So here you need to find first the diagonal matrix of a given matrix. So the procedure, let us look at the procedure once again. So first you need to find the eigenvalues for a square matrix A. Then you have to find the eigenvectors to get the modal matrix P. Then you need to find the diagonal matrix, which is D, by the formula of D. The formula of this D is equal to P inverse AP. So by this formula you need to find out the diagonal matrix, and then you need to obtain A raised to N by the formula, which is A raised to N is equal to P into D raised to N into P inverse. So let us again take the same example which we have discussed earlier. So for a given matrix A, which is 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3, calculate A raised to 4. So since we have solved this problem, we have solved this matrix for the eigenvalues and eigenvectors, as well as we have used the same problem in order to calculate the diagonal matrix, and therefore we know that the modal matrix of this matrix is the group is obtained by grouping the eigenvectors. We have already calculated the eigenvectors of this matrix, so you can refer the previous lecture for that, and that modal matrix will be equal to this, which is 1 2 2 2 1 minus 2 2 minus 2 1, and you know, the inverse of this modal matrix P inverse is 1 by 9 into 1 2 2 2 1 minus 2 2 minus 2 1. Then the diagonal matrix have also been found, and you know that the diagonal matrix is nothing but a matrix in which the eigenvalues are present on the principal diagonal and the rest of the elements are 0. So we have already calculated the eigenvalues for this matrix, which are 0, 3 and 15. So the diagonal matrix is 0, 0, 0, 0, 3, 0 and 0, 0, 15, and hence this a raised to power 4 will be equal to, the formula for finding a raised to n is p into d raised to n into p inverse. So here, since we have to calculate a raised to power 4, so it will be p into d raised to power 4 into p inverse. So let us substitute here these matrices. So this p is the modal matrix, so we substitute here this p as the modal matrix over here. Then d raised to power 4, so d raised to power 4 will be equal to 0, 0, 0, 0. Then 3 raised to power 4 is 81, 0, and here it will be 0, 0, and 15 raised to power 4 is 50,625 into 1 by 9 times p inverse. So here this p inverse will be this, which is 1 by 9 into 1 to 2, 2, 1 minus 2 and 2 minus 2, 1. So that a raised to power 4 will be equal to, I keep this first p as it is and take the multiplication of these two, that is multiplication of d raised to power 4 with p inverse. Then this is the matrix, multiplication of the two matrices. Then I will have the product of the matrix which is p with the matrix which is d raised to 4 into p inverse. So by this way we can solve this matrix, and we get the value of a raised to power 4, which is the answer. Then the next method is the Sylvester theorem. By using this theorem, we can also find the power of a matrix in very simple steps, because though this is the conventional method, but it becomes too lengthy, because first you need to find the eigenvalues, then you have to find the eigenvectors in order to get the modal matrix, then you need to find the diagonal matrix, and then by using the formula, that is a raised to power n, which is equal to p into d raised to n into p inverse, you need to find the power of the matrix. And the process becomes very lengthy. So in order to solve the problem, to find the power of a matrix, we use the method. We can also use the shortcut method, which is based on the theorem, which is the Sylvester's theorem. So let us look at the Sylvester's theorem. Then if this p of a is equal to c0 into a raised to n plus c1 into a raised to power n minus 1 plus c2 into a raised to n minus 2 and so on up to cn I, where this p of a is a polynomial, where this c0, c1, c2 and so on, they are constants, and if determinant of lambda I minus a is equal to f of lambda, and the adjoint of a matrix which is lambda I minus a is represented as the matrix of f of lambda, then this z of lambda will be equal to the adjoint of the matrix of lambda I minus a, which is f of lambda, divided by f dash of lambda, where this f dash of lambda is the derivative of f of lambda. So that will be equal to adjoint of the matrix which is lambda I minus a divided by f dash of lambda. So this is our z of lambda. Then according to the Sylvester's theorem, this power of a will be equal to p lambda 1 into z lambda 1 plus p lambda 2 into z lambda 2 and so on, where this lambda 1, lambda 2, lambda 3 and so on, they are the eigen values. So let us take one example from which you will have a clear idea about how to find the power of a matrix. So let us take a matrix A, which is a 2 by 2 matrix, say 2, 0, 0, 1, and you have to find the power of the matrix such that you have to find a raised to power 100. So now our f of lambda is equal to determinant of lambda I minus a. So this will be equal to lambda minus, this will be lambda 0, 0 lambda minus determinant of our matrix, which is 2, 0 0 1, so that will be equal to lambda minus 2 0 0 lambda minus 1. So this f of lambda will be equal to lambda minus 2 into lambda minus 1, and that should be equal to 0. So from this equation we get the roots of the equation as lambda 1 is equal to 1 and lambda 2 is equal to 2. So these are our eigen values. So lambda 1 and lambda 2, these are the two eigen values of our equation, which is lambda square minus 3 lambda plus 2. So this is nothing but lambda square minus 3 lambda plus 2. This is our f of lambda. So we can calculate the let us differentiate this f of lambda. So we get f dash of lambda. So f dash of lambda will be equal to 2 lambda minus 3. So this is the derivative of this f of lambda, which is equal to 2 lambda minus 3. So f dash of 2, so f dash of 2 means here if we substitute the eigenvalue as 2, then it will be 4 minus 3, which is equal to 1, and f dash of 1 will be equal to 2 minus 3, which is equal to minus 1. So these are our values of f dash of 2 and f dash of 1. Then the matrix f of lambda is the adjoint of the matrix of lambda I minus a. So for this z of lambda 1 will be equal to z of 1, because this is our first eigenvalue, and it is equal to the matrix of f of 1 upon f dash of 1, which is equal to now since this f dash of 1 is equal to minus 1, so I write it as 1 upon minus 1, and this 0 0 0 minus 1 is nothing but it is the adjoint of the matrix of lambda I minus a for the value of lambda as 1. You know how to find the adjoint of a matrix, which is a 2 by 2 matrix. So since here I will give the solution for the first one, that is our matrix lambda I minus a for the value of lambda as 1. For lambda as 1, it will become 1 minus 2. So 1 minus 2 is minus 1, 0, and 0, then 1 minus 1, that is 0. So this is our matrix, which is lambda I minus a for the eigenvalue, which is 1. Lambda is equal to 1. Then you need to find the adjoint of this matrix A. So this is our matrix, which is lambda I minus A for the value of lambda as 1. Then you need to find the adjoint of this matrix, and you know how to find the adjoint of a 2 by 2 matrix. So for finding the adjoint of a 2 by 2 matrix, so for adjoint of 2 by 2 matrix, you know the process that you need to find the cofactors of a11, then a12, then a21 and a22. So here this is a shortcut method to find the adjoint of a 2 by 2 matrix. So here look at the sum. Here 1 plus 1 is 2, so it is even, and therefore the sign of that cofactor will be positive. 1 plus 2 is 3, which is odd, so the sign will be negative. Here it is again 2 plus 1, it is odd, so it is negative, and 2 plus 2, it is positive. So these are the signs for the cofactors. Then for the cofactor, which is a11, you have to delete the first row and first column, so you will get the cofactor of this a11 as 0. Then the for second cofactor, which is a12, you have to delete the first row and second column, so again you will get the cofactor as 0. Then for the third element, which is a21, you have to delete the second row and first column, so here it will be equal to minus 1. And for a22, you have to delete the second row and you have to delete the second row and second column, so this will be this will be minus 1. So second row and second column, so it is minus 1, and this is second row first column, so second row first column, so this is again 0. Yes. So now the matrix of cofactors of this lambda I minus a for the value which is lambda is equal to 1, it becomes this as 0, 0, 0, 0 and minus 1. So this is the matrix of cofactors of this matrix. Then in order to find the adjoint, you have to take the transpose. So even if you take the transpose of the matrix, again the matrix will be the same. So this is our transpose matrix. So this is our adjoint of the matrix, which is lambda I minus a for the value which is f of 1. So that is 0, 0, 0, 1, and this should be divided by 0, 0, 0 minus 1. It should be divided by 1 upon minus 1 because f dash of 1 is equal to f dash of 1 is equal to minus 1. So this will be finally equal to 0, 0, 0 and 1. Similarly, you can follow this method to find the adjoint of the matrix which is lambda I minus a for lambda to be equal to 2, and you will observe that it is equal to this 1, 0, 0, 1. So this is the adjoint of the matrix of lambda I minus a for the value of lambda to be 2, and so that is our matrix which is f of 2, and it is divided by f dash of 2. So here f dash of 2 is equal to 1, so it will be 1 upon 1 into 1, 0, 0, 0. So these are my values of z of lambda 1 and z of lambda 2. So by Sylvester's theorem, this P of A will be equal to P of lambda 1 multiplied by Z of lambda 1 plus P of lambda 2 multiplied by Z of lambda 2 and so on. So this A raised to power 100 will be equal to P of lambda 1 is lambda 1 raised to power 100 into because this P of lambda 1 is nothing but it is the eigenvalue which is lambda 1, and you have to take the power as 100, so it is lambda 1 raised to 100, and then you have to substitute here z of lambda 1. So z of lambda 1 is equal to 0, 0, 0, 1. So that is 0, 0, 0, 1 plus second eigenvalue which is lambda 2 raised to 100. P of lambda 2 is second eigenvalue raised to n. So it is lambda 2 raised to 100, and then you have to substitute here z of lambda 2 which is 1, 0, 0, 0. So it is 1, 0, 0, 0, and therefore this a raised to power 100 will be equal to the first let us substitute here first eigenvalue lambda 1 is equal to 1, so it is 1 raised to 100 into 0, 0, 0, 1 plus lambda 2 is 2, so it is 2 raised to 100 into 1, 0, 0, 0. So if I take this inside, then it will be 0, 0, 0, 1 because 1 raised to 100 is again 1 plus if I take this inside, then it will be 2 raised to 100 0, 0, 0. So finally if you add these two matrices together, then this a raised to power 100 will be equal to 2 raised to 100 plus 0, 0, 1. So this is the answer. So let us look at this Sylvester's theorem again. First, what you have to do is you have to find f of lambda, which is the determinant of lambda I minus a. Then you will have the equation for f of lambda as a quadratic equation, which is lambda square minus 3 lambda plus 2, for which you will get the roots of this characteristic equation as lambda 1 and lambda 2, which are the eigenvalues. Then you need to find the derivative of this f of lambda as lambda dash. Then you have to find out f dash of the two eigenvalues. So f dash of 2 is this, f dash of 1 is this. Then you have to find the matrix of f of lambda, which is adjoint of the matrix of lambda I minus a. So your z of lambda 1 will be equal to z of 1, which is the adjoint of a matrix which is f of 1 divided by f dash of 1. So that you will get z of lambda 1, and z of lambda 2 will be equal to z of 2, which is equal to matrix of f of 2 divided by f dash of 2, where this f of 2 is the adjoint of the matrix which is lambda I minus a for the eigenvalue which is lambda 2. Then by Sylvester's theorem, this P of A is equal to P into P of lambda 1 into Z lambda 1 plus P of lambda 2 into Z lambda 2. So this A raised to 100 will be equal to here P of lambda 1 is your eigenvalue 1, which is lambda 1 raised to 100 into this Z of lambda 1 plus lambda 2 raised to 100 into this Z of lambda 2, and then by solving this we'll get the answer. Then next is the exponential of a matrix. So to find the exponential, that is e raised to power a, we know that we can expand this e raised to power x as 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So this e raised to power a can be expanded as 1 plus a square by 2 factorial plus a cube by 3 factorial and so on. So here, in order to know the exponential of a, we are going to need the terms of a square, a cube and so on. So here we are going to need the powers of the matrix, and you know how to find the power of a matrix, that a raised to power n will be equal to p into d raised to power n into p inverse, where this p is the modal matrix, d is the diagonal matrix, and p inverse is the inverse of the modal matrix. So this e raised to power a will be equal to p into summation over n is equal to 0 to infinity. Here we can write down this expansion as d raised to power n upon n factorial into p inverse. So this d raised to power n will be equal to, since this is the diagonal element, d is the matrix of diagonal elements, so it will be d1 0 0 d2, and this should be raised to power n, so it will be d1 raised to n 0 0 d2 raised to n. So that it will be equal to p into matrix. This is summation over n is equal to 0 to infinity. This will be d1 raised to n upon n factorial 0 0 summation over n is equal to 0 to infinity d2 raised to n upon n factorial into p inverse. So in general, you can directly remember that e raised to power a will be equal to p into the matrix of e raised to power d1 0 0 e raised to power d2 into p inverse. So again, let us take the same example which we have discussed earlier for the matrix A, which is 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. Find e raised to power a. Find the exponential of this matrix A. So we know that we have already calculated what are the modal matrices. So modal matrix for this is 1 2 2 2 1 minus 2 2 minus 2 1, and the inverse of this modal matrix we have also calculated it, and we have also find out what is the diagonal of this matrix. So this e raised to power a will be equal to p into d d raised to power this this e raised to power a will be equal to p into e raised to power. Here you have to write down the eigenvalues as 0. So this will be p into e raised to power 0 0 0, then it will be 0 into e raised to power the second eigenvalue, which is 3 0, then 0 0, and e raised to power here the third eigenvalue, which is 15 into p inverse. So that will be equal to, I keep this first modal matrix p as it is, then multiply this d raised to power n with the p inverse. So this, by solving this, we get this matrix, and then I will have the multiplication of this modal matrix p with the product of d raised to n into p inverse. So finally, by solving this, I will get the answer as this, which is 1 by 9 into 1 plus 4 e cube plus 4 e raised to 15 and so on. So this is e raised to power a, where a is our matrix, which is 8 minus 6 2. So e raised to power this 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 is equal to 1 by 9 times this matrix. So This is a problem which we have taken as an example of a 3x3 matrix, because we have already calculated the modal matrix, inverse matrix and the diagonal matrix for this matrix. Hence we have taken the example of a 3x3 matrix to find the exponential of this matrix A, which is a 3x3 matrix. But in exam usually there is no question on a 3x3 matrix to find the exponential of a 3x3 matrix, but it is usually asked for the 2x2 matrix, that is exponential of a 2x2 matrix, which becomes quite easy as compared to this one. But we have discussed the complete process, so you can easily apply this method in order to solve the exponential of a 2x2 matrix as well. Okay, so please provide a review for the course if you like it. You can do this by visiting the review section as shown below. You may also ask questions in the comment section of a lecture, which will allow us to serve you better. Thank you.